Hello, my name is Jason, and this is my recording for homework 3. I'll start with the Jupyter Notebook. Here is where I import the libraries used in this project. NumPy and Pandas are used for handling the dataset. Matplotlib is used for plotting results. From skitlearn, I import functions for splitting the dataset and encoding labels. From TensorFlow Keras, I import the neural network tools, including the tokenizer, sequence, padding utilities, and the layers used to build the RNN and LTSM models. And moving on, here, this is where I upload the dataset into the Colab environment. The dataset is the Twitter US Airline sentiment dataset, which contains tweets about airline experiences along with a sentiment label. And in the next dataset, this is where I did the text cleaning. I clean the tweets before training the model. I convert text to lowercase, remove URLs and Twitter mentions, remove special characters, and remove extra spaces. This reduces noise and helps the model focus on meaningful words. Okay, here I did label encoding. The sentiment labels are categorical, so I convert them into numerical values using label encoder. The three classes in this dataset are negative, neutral, and positive. And moving on, next I split the dataset into training and validation sets using the 80-20 split. I also use stratified sampling so the class distribution remains consistent between the datasets, the two sets. And this is where I did the tokenization. I convert the tweets into sequences of integers using a tokenizer. Each word in the vocabulary is assigned a unique index. Here we do the padding. Since tweets have different lengths, I pad all sequences to a fixed length of 30 words. And padding ensures every input to the neural network has the same size. And here we have one-hot encoding. Each word index is converted into a one-hot vector. Since the vocabulary size is 2,000 words, each word becomes a vector of length 2,000. This representation allows the network to process categorical word inputs. Here's an example output. Here I display an example tweet along with its padded sequence and one hot encoded shape to verify that the pre-processing pipeline works correctly. And this function here defines a baseline simple RNN model. The architecture includes a simple RNN layer, dropout for regularization, a dense layer with ReLU activation, and a final softmax layer with three outputs for the sentiment classes. And this function, here I trained the simple RNN model for 10 epochs using the training dataset and validate it on the validation set. Um, these plots show training validation accuracy and loss over time. Training accuracy increases steadily while validation accuracy levels around the mid 70%. Here I evaluate the simple RNN model on the validation set and calculate the final validation accuracy. And this classification report shows the precision, recall, and F1 score for each sentiment class. Negative tweets are classified mostly accurately, while neutral tweets are more difficult to predict. Here, to improve performance, I run several experiments where I vary different parameters such as the number of RNN layers, the number of dense layers drop out rate, O2 regularization, and learning rate. Here's the experiment results. The results of the experiment are stored in a table and sorted by validation accuracy. This allows us to identify the best performing configuration. Next, I build on the LTSM model. LSTM networks are designed to capture longer dependencies in sequential data and help address the vanishing gradient problem in standard RNNs. Here I train the LSTM model using the same dataset and training settings, so the results can be fairly compared with the simple RNN model. Here's a final comparison. Finally, I evaluate the LSTM model and compare it to the simple RNN model. The LSTM achieved higher validation accuracy, showing improved performance on the sentiment classification task. And that's all for the Jupyter Notebook. Here we have the slides. Okay, so this project analyzes sentiment classification of airline tweets using recurrent neural networks. The goal is to compare the performance of simple RNN and LSTM models. Problem. The task is to classify tweets into 3 sentiment categories: negative, neutral, and positive. This is a sequence classification problem because tweets are ordered sequence of words. Dataset. The dataset used is the Twitter US airline sentiment dataset from Kaggle. It contains over 14,000 tweets discussing airline experiences. Data preprocessing. The tweets are cleaned by removing URLs, mentions, and special characters. After cleaning, the text is tokenized and converted into a numerical sequence. Tokenization and padding. Each tweet is converted into a sequence of words, indices, and padded to a fixed length of 30 words, so the neural network receives consistent input dimensions. One-hot encoding. The integer word indices are converted into one-hot vectors with a vocabulary size of 2,000 words. Training setup. The dataset is split into training and validation sets. Using an 80-20 split, the models are trained for 10 epochs. Simple RNN architecture. The baseline model uses a simple RNN layer followed by dropout and dense layers with ReLU activation, ending with a softmax output layer. Simple RNN training results. These graphs show training and validation accuracy and loss. Training accuracy increases quickly while validation accuracy levels off. Simple RNN performance. The simple RNN model achieved a validation accuracy of approximately 73%. Experimental design. To improve performance, multiple experiments were conducted by varying RNN layers, dense layers, dropout rate, regularization, and learning rate. The results. This table shows the results of those experiments. The best configuration improved validation accuracy to around 78%. LSTM model. An LSTM model was implemented because LSTMs are generally better at capturing long-term dependencies than sequences. This is the LSTM architecture. The LSTM architecture is similar to the simple RNN model, but replaces the recurrent layer with an LSTM layer. The LSTM model achieved higher validation accuracy and more stable training behavior. Model comparison. Comparing the two models, LSTM outperforms simple RNN with a validation accuracy of approximately 77 to 78%. Overfitting and generalization. The simple RNN model shows signs of overfitting since training accuracy becomes much higher than validation accuracy. And to conclusion, both models can perform sentiment classification effectively, but LSTM provides better generalization and higher validation accuracy.